All right,
Yeah.
so this is dealing with transition metals and coordination compounds. Complexes is specifically what we're going to focus on. And our goal is to get to crystal field theory, and crystal field theory explains a lot of why we see the different colors that we see. So, a couple examples here. Which one of these are the emerald, and which one's the ruby?
The bottom one is the emerald.
All right, and the top one is the ruby. So we know rubies are what color? Red. Emeralds are green. What color is a sapphire?
Blue.
Okay. What colors is quartz?
Something like clear.
Yep. Yep. What color is amethyst?
I'm not sure.
Purple.
There you go. What color is aquamarine?
Blue.
Yeah, if you guys get that one wrong, I'm gonna throw a book at you. It'll get through the monitor, don't worry. It's blue. Aquamarine. Aqua is blue, right? Yeah.
Yep.
Oh yeah. Right.
There's
So now here's the thing. So when we talk about minerals and crystals, the colors that you see are oftentimes caused by interactions within the crystal structure, the complexes that form. So when we talk about rubies, all right, the corundum is aluminum oxide, and ruby is a part of the family corundum. And so corundum has a formula of Al2O3, aluminum oxide. It's very simple. Now, what happens is that if there is any chromium present while the crystal is growing, that chromium will replace the aluminum. And when it replaces the aluminum, it actually changes the color of the crystal because of the way that transition metal interacts inside the crystalline structure. And so in turn, our eyes see the red color that comes out. Same thing with the emerald. Now, emeralds are this is a crazy formula, but beryllium, aluminum silicate. That's what this would be called. And so the aluminum here is also replaced by the chromium. Now, what you should find interesting is that shouldn't it give you the same colors here? No, the chromium is actually interacting a little differently, and so you end up getting a green color. So all emeralds are actually a part of a family that's called the beryl group. And the beryl family has several different colors of crystals that can form. Emeralds are by far the most notorious and popular within the group because they're green. They're very rare to come by. But I'll give you this. All the emeralds that you buy from a jewelry store are man-made. They're not actually real emeralds. If you were to buy a real faceted emerald that nature grew, it would cost you 10 to 15 times more than what you're going to pay for the lab grown emerald. And most of the gemstones that you buy at a jewelry store are man-made anyhow. I don't know if you guys knew that or not. There's a few that are not because they can't reproduce them, but emerald is one of those that they can reproduce, and they can produce some fantastic crystals in the lab. So kind of like what we did in our crystal growing project. So aquamarine is blue. Now what's interesting is aquamarine is in the same family as an emerald. Okay, it's in the beryl family. Now aquamarine are blue, and so aquamarine's being blue. In fact, let me see here. I bet you I took that picture off of here. I thought I had a picture. Let's see if I have one in here. Oh yeah, here we go. So this is a picture of an aquamarine I have. So see how blue that is? Now here's my thoughts on this one, okay? So obviously there's going to be some replacement of the aluminum ion in the structure. The question is what transition metal replaces it? Now here's the thing. Francis, I'm asking this. I'm going to ask you a question. I want you to answer this question. You ready?
Okay.
What color is iron?
Isn't it silver?
Yeah, exactly. Brianna, do you agree with him?
Yes, like a dark gray, I would
Yeah,
go.
that's perfect. Now, what if I told you that the aluminum was replaced by iron in this crystal? That's what gives aquamarine its color, is that the aluminum is replaced by iron, and iron is what gives you the blue color. Now, on the same note, let's see here. I don't know if I have an amethyst in here. Here's an emerald. This is my emerald. I took this picture here. So this is a North Carolina emerald too, by the way. This is about 2 inches tall, just so you have a size reference. But this crystal is worth a good bit of money. Oh, what? Here's another aquamarine. Now, here's a New Jersey rock, which I think is pretty cool. So you got a whole assortment of colors here, but this is under black light. This is not caused by the same phenomenon. This is caused by the electrons being excited. So you got to be careful there. And I think I may be out of luck with my amethyst. Out of all the pictures I have, I do not have a picture of an amethyst. Don't that just drive you crazy? No, y'all probably don't care. Well, shoot. And I just took all my documents out because I don't have any space on this crazy computer. Anything here? I really want. Oh well. So much for that.
It's a big spider.
What?
I saw you had like a picture of a big spider or something like that.
Oh yeah, yeah. That's my pet.
Oh man.
I brought the spider in, and now she's living in an aquarium, and she just laid eggs yesterday too.
Oh wow.
Yeah, she's a big spider.
Yeah.
I thought she was dead,
Oh yeah.
and she ended up waking in my hand. She wasn't dead. Here we go. This is just an example. See the purple color?
Yeah.
So the quartz is silicon dioxide. So 1 silicon and 2 oxygen. But what happens here is that in the solution as it's growing, the silicon is replaced by an iron. And iron is what gives you the purple color in the quartz crystal. Now you think about it, purple and blue, aren't they in a similar shade area, the same group of color?
Yes, they are.
Yeah, so makes sense in that case. And there you go. So that's a calcite clamshell, by the way. See the shell and the calcite that's on it, it replaced and as it fossilized. So this is a fossil. When you put a black light on that, it turns it to a white color. It's actually really cool looking.
Oh wow.
Yeah. So going back here, all right, so let's get into some transition metal and properties. So this goes back to your 151 part where we talked about periodic trends. So let's see if I can, let's see here. Do I have them right here? Nope. Okay. All right, so I want to just kind of review that real fast with you here. So this will take just like a minute or two at most. This is stuff that you should remember. Most people typically remember this. All right, so there's atomic radius. There's ionization energy. And then there is electronegativity. Those were the 3 main periodic trends that we talked about. So I'm going to talk about atomic radius for now. All right, this will be a quick and easy thing. So I'm going to draw an arrow. So the atomic radius increases in this direction. Now the ionization energy increases in the opposite direction. So increases this direction. I'm not going to go into details why. I'm just going to put it out there to you. All right. and electronegativity increases in this direction. So this is what we learned in 151. So as you go up and to the right, the size decreases, but the ionization and the electronegativity increases. So size is very important to how the atoms interact with each other. So fluorine, being one of the more smaller elements on the periodic table, has one of the highest electronegativity values, and therefore it's not going to be willing to share its electrons. It's stingy and it wants to keep its electrons. Whereas cesium would be far down to the left here. Cesium is the complete opposite. It's a very large atom. It doesn't care. It just gives away its electrons. So here, take it. You can have it. And so now, as we talk about that, that's just something you got to keep in the back of your head. We never talk about the transition metals, okay? So this was a group that we never looked at. We focused on the main group elements in 151. Now, in 152, we're going to focus on the transition metals. That's what this chapter is all about. So keep that in the back of your head as we dig into this. Now, I'm not going to sit here and wait for you to write every slide down. I'm not doing it. You can actually go onto Moodle, find this PowerPoint, and you can jot down the notes or just have the PowerPoint present. It doesn't matter. So, but I'm going to go through these slides fairly quickly. I want to get through this stuff so we don't waste any more time. So the properties of transition metals are similar to each other and are very different from the properties of the main group elements. So we're good. We've got to get that figured out in our head right now. It says right here in the first statement that they're very different from the properties of the main group of metals. And that's why we didn't talk about them in 151, because it would have confused you. We don't need that. So, but for here, you're growing up, you're a little bit older, you can handle it. So that's why we're doing it now. So the first thing is they have high melting points, high densities, moderate to very hard, and good, very good electrical conductors. Francis, take a fork and stick it in the outlet and tell me what happens.
I'm going to get electrocuted.
Exactly, yeah. You're not going to do that, are you? You know better. Metals are very good conductors of electricity. Now, take the oxygen gas and stick it in the outlet and see what happens.
Nothing happens.
Right, because they're not good conductors of electricity. So on that periodic table in the middle, the arrows that you would draw would be inward. So as you go in towards the middle on the transition metals, so let's say iron is in here and osmium's down here. So these elements that are present, these have the highest melting points, high densities, and these are some of the best conductors of electricity. So think about your old light bulbs. Your old light bulbs are actually composed of tungsten filament in it. So that old style light bulb, that little thing that comes up and is real squiggly like, that metal right there is tungsten. And tungsten conducts electricity, but it also heats up. As it heats up, it gives off light that we can use to do our everyday activities at nighttime. So it's pretty cool. So that's the first couple details about transition metals. The second thing is the similarities and properties come from similarities in valence electron configuration. They generally have two valence electrons. So when you draw the electron configurations, how many of you remember doing electron configurations 151?
I remember it.
All right. Just one person. Brandon, do you remember it?
I said, yeah, probably didn't pick up though.
I would like to see an example because it's been since the springtime.
Okay. All right. So let's say we have iron. What we got to do here is, I don't want to keep that right now. So go back here. I need a periodic table here. If I can find it here. Okay, here we go. All right, this is perfect because you see this configuration. So the periodic table is broken up into S, D, P, and F groups. Remember that?
Yep.
All right, so what you need to do is get your periodic table out, and then we'll kind of go through some of the configurations here. So I'm going to copy that, go back here, go here. Let's go on the page here. There we go. All right, now we'll just knock out a couple things here that we're going to see show up here. So iron is right here, okay? So what we're going to do is we'll just put numbers here. 1, 2, 3, 4, 5, 6, 7. So iron has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. So 3d6. That's the configuration for iron. Now, the question is, how many valence electrons does iron have? All right. So that's the question. So what we do is we look at the last S and P. Now, there is no P, so we don't worry about that, but we do look at the S. We don't look at 3p6 because we need our S and P to be the same value, the highest energy value. So in this case, it's 4s2. So there's 2 valence electrons for iron. All right, so that's the first thing we look at here, okay? Now, if I talked about, let's look at silver, okay? So silver is right here. So I'm going to draw the noble gas configuration. So silver is most like krypton. So we're going to put krypton in brackets here, and we're going to have 6s2, 4f14, 5d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 5d9. Now remember that the lanthanide series comes down here. That's why I introduced the F group here. All right. So now we look at this configuration and say, okay, how many valence electrons does silver have? Well, there is no P, so there's nothing there, but there is S, and there's 2 in the S orbital. So it's 2 valence electrons. Now, all transition metals are going to have that same configuration. All transition metals have 2 valence electrons. All right. So that's a rule of thumb to remember. Now, the question is that as we talked about transition metals before, we look at charges of transition metals. So iron can be +2, +3, +4, etc. And so these transition metals can have different charges because of how their electron configurations are written. And that's what I want to talk about in just a minute. Brianna, does that make sense? Does that kind of help remind you?
Yes, thank you.
Yeah. Now, if you still need any more help, feel free to go onto my channel and go find the electron configurations video, okay? All right, so here's we're talking about the way they're written out. I'm not going to get in detail, just did that. We know that because the sublevel splitting force, let energy 3D and the force fills before 3D. So this is important detail, okay? So 4S will fill before the 3D. However, the difference in energy is not large. Some of the transition metals have irregular electron configuration in which the NS only partially fills before the other. So the electron configuration sometimes are not the same as what they theoretically should be. So here's some examples here. What I would do is take a picture. Well, you can take a picture of this, or you can just print off the slide from the PowerPoint, whichever is easiest for you. But so if we look at chromium, chromium is expected to be 4s2, 3d4. So if I go back to this chart here, all right, so chromium is here. All right, so it's 4s2 and then 3d, 1, 2, 3, 4. So it's 3d4 there. So that's the way we would normally write it out. That's fine. But the reality of it is that chromium is actually 4s1, 3d5. Now the question is, why is it 4s1, 3d5? So I'm gonna explain that to you right now. Okay, so So 4s1, 3d5. So that's configuration. Don't forget the transition metal in front of it. But so when we look at our orbitals, remember you have S and this is D. So these little lines represent an orbital. Remember, you can have only 2 electrons per orbital, and then they fill up in this fashion here. So you can have a total of 10 electrons in the D group, 2 electrons in the S group, and in the P group, you have 6. How many of you are deja vuing right now with what I'm talking about? How many of you remember this?
I remember this.
All right,
It's been a
so
while.
yeah. Now, if we take chromium, initially it's 4s2, 3d4. All right. So if I draw the configuration here out, it's going to be 1, 2, 1, 2, 3, 4. Now, if you look at this, you see that there's an open shell over here, the d orbital. Okay, so there's open orbital, and sometimes what happens is that when you put this extra electron right here, even though it fills in first, it's more unstable, and so what an element might do is it might, and elements they do this, they're free to do this. They can move their electrons around. Now each of the orbitals have their own electron. You haven't changed the number of electrons, you just changed the configuration of it. And so this would be 4s1, 3d5. So this is a lot more stable than the previous transition metals configuration. Does that make sense, guys? So this is more stable, and that's why it does that. So, and there's just a few of them that does this, because chromium is one, copper is the most notable. That's what I learned when I was in class. Then we have these other 3, which we don't really focus on, but you can see the configurations over here, what they actually are compared to what you would write down, based off the way we learned it in class. So we have these oddball electron configurations, and so remember, all that's about the stability of the atom. Now we talk about size. Okay, so here we get into atomic radius. Now we've already talked about the fact as you go from right to left and top down, the size increases. So on the bottom left hand side is large, on the top right is very small. Now as we look at the size for the transition metals, the atomic radius of all transition metals are very similar. There's small increase in size down a column. So now what we should see happen is this: as we look at the periodic table, and remember, we're only focusing on these groups here. So this is the first, second, third row transition metals. Okay, so as we go down in the rows, what we should see is that the atomic size should increase. Okay, so we're going to focus on the graph specifically here. So the first row is blue, it's small, and then the second row is red, and as you can see, the radius increases. So that's true. All right, the size of the atom increases as you go down into the next period in the second row transition metals. Now, if you go down to the third row, shouldn't it be larger? Well, technically it should be. But if we look here, what we see is the third row is actually fairly similar to the second row. It doesn't increase, it stays the same. The question is why? The answer is right here. It's called Lanthanide contraction. All right, so this is something that you do want to make sure that you at least jot down. So you got to know what lanthanide contraction is. All right, so this is the explanation as to why we see the third row not increasing consistently as we see in all the other rows of the periodic table, and more specifically the transition metals. Okay, so it's all about lanthanide contraction. So lanthanide contraction is the decrease in expected atomic radius for the third transition metals series atoms that come after the lanthanides. All right, that's why we remember La is lanthanum. That's where the lanthanide comes from. It's the lanthanum element on the periodic table. So if I look here, you have La here. So, and then all the other elements follow suit with that. And the same thing for the 7th period. We don't really look at the 7th period because most of them are going to be man-made, but these in the 6th period are actually elements that exist in nature. We can find these elements. So, and we do use a lot of them. So we use tungsten as in our light bulbs. We use iridium in our spark plugs. We use platinum in our catalytic converters. We use gold. Gold is the precious. That's your money maker. And then we have mercury, which used to be used in thermometers. And mercury can also be used in catalysts too. So, but this particular row is very important. Now, so going back to the PowerPoint here. So lanthanide contraction. So now, when we talk about the lanthanide series, well, guess what? You have the F group. Now, what's important about the F group is that these elements are very large to begin with. Okay, so that's the first thing. The F electrons are far away from the nucleus, okay? So we talked about shielding electrons in 151. So this is the nucleus here, and the nucleus is positive. So you have your orbits around it where the electron exists in. The F group is way on out here, okay? So the F group is way far out there. So you have this much distance between the nucleus and that electron cloud. Now, the orbitals in that electron cloud. So the F orbitals specifically. Since the F group is so far out, the F electrons do not factor in on the shielding of the nuclear charge. So they don't have much precedence on neutralizing that large positive charge in the nucleus. So what happens are the valence electrons that are in the outer shell here. So the valence electrons are actually going to be pulled inwards because of the attraction that they have with that strong positive nuclear charge. And so that's what we call it, the lanthanide contraction. All right, it's because of that, the F electrons not being very good at shielding the valence electrons. So as a result, the valence electrons get pulled closer to the nucleus. That's why the radius in the 3rd row transition metals are not increasing as they should. It's because of the lanthanide contraction. You do need to make sure that that's something that you understand. Any questions on that before I move on?
I think I understand it.
All right, so next is ionization energy. So ionization energy follows suit with the radius. As the radius gets larger, the ionization energy should get smaller. You can see that pattern is sort of showing here. Remember, there's not going to be much change in here because you're dealing with those D and then the F electrons. But what you do know, since you have that lanthanide contraction show up in the 3rd row, the 3rd row's ionization increases, whereas it should have been decreasing. It is actually increasing because of that lanthanide contraction. So it shows up yet again in the other configuration or in the other periodic trend. So that's important to understand here, and it shows in that graph. I love the graphs here because they say a whole lot about what's happening. Electronegativity again. All right, so as the atom gets larger, the electronegativity should get smaller. And so as we go from the 1st row to the 2nd row, we don't see that getting smaller. And then we get to the 3rd row and oh my gosh, the electronegativity value actually increases more. And this element specifically is very important because this is gold. Gold is one of the most precious elements on Earth. Gold is one of the least reactive elements on Earth. If you go back and look at your standard reduction potentials table, you're going to find gold being at the bottom of that chart, which, well, in this case, when we talk about activity series, gold is the least active element on the periodic table. And that's because gold has one of the highest electronegativity values. I think it's like 2.9 or something like that. On the, yeah, I can actually look at here. So electronegativity is actually 2.4. So hydrogen is 2.1. All right, so keep that straight. Hydrogen is fitting in between boron and carbon. And I think carbon, I can look this. So these values that I'm looking up right now that I'm talking about are actually found in the textbook in chapter, I want to say 8 or 9. So I'm gonna tell you what. So I'm gonna find it real fast here. Let's see here. It's chapter 9, by the way. Right, here we go. This is getting close. You can never find it. All right. So as I'm trying to find the electronegativities here. Let's see. 0.6396. Here it is. All right, so remember that carbon's gold is 2.4, carbon is 2.5. Carbon's a nonmetal. Carbon's in the very top right-hand corner. Carbon is one of the smaller elements on the periodic table. Gold is one of the larger elements, but its electronegativity is about equal to that of carbon. So that's really interesting because of it being with transition. Typically metals are free to give their electrons away, but gold is not so much. If you wear a gold necklace or a gold ring or gold earrings, it will never change shape or color. It will not doesn't matter how much you sweat or anything, because of the fact of it having that high electronegativity value. It's not going to change. It's one of the least active elements on the periodic table. And that's what makes it so unique. When you pull gold out from underground, it still looks like gold. You can tell gold moreover than anything else out there. Yeah, gold is just one of those elements that does not change. And that's what makes it highly sought after. Now, platinum is another one. Platinum is on up there too with its electronegativity, but not as high as gold. So very interesting to see that pattern show up. Now, what, Francis?
I said, is platinum a strong metal, or is it really
platinum is a pretty, well, we call it inert. Inert means it will not react. Platinum is used in a lot of different places. So your car's catalytic converter has platinum as the catalyst. It does not change. That's why people steal catalytic converters, because it has platinum in it. Okay. And platinum is used in electrolysis. Platinum is used as the electrodes because platinum does not break down. That electrode will always stay the same no matter how much energy you put through it. So very unique metal. It's very precious, very expensive. So this chart, I'll let you guys look at this chart. This chart talks about the charges of the metals, okay? The iron, we talked about iron earlier, having +2 and +3. All the red colors you see here are the common oxidation states for these elements. The other color, the brown one, is the less common. You don't see this very often. So iron has 2 that are common, but it actually has 5 different oxidation states. The other 3 is not something that we come across very often. All right, chromium has +3 and +6. All right, if you took my 151, you know that because we talked about chromium. Chromium is very unique. +3 gives you green, +6 gives you orange. And so the oxidation state that you're looking at gives you different colors. All right, so every one of these is true. Copper +2 is blue, copper +1 is green. Let's see if I can find an example here for you right fast. So copper, it can be in 2 different minerals. So malachite and azurite. So if we look at this, let's get some pictures pulled up here. All right, if we look at, this one's a good example here. So you see the blue, which is azurite, that's the copper +2 ion, and you see the green on the outside, that's malachite, which is +1. That's how you can tell the difference between the oxidation states. It's all about the color of the ion. All right, now that leads us into complexes. So I'm going to get through the next couple slides here, and then we're going to call it a day. So complexes are when you have a metal ion found inside of a complex, which is surrounded by, let's say, water molecules, okay? So let's say you put copper 2 chloride in the solution, the copper +2 goes in the solution, then you're going to have water molecules surrounding the copper ion. And what they're doing here is they're actually forming a complex. You have these bonds that form in between the copper and the water molecules. So this would be considered a complex. So you have the metal ion, which is in the middle here, and then you have the waters attached to it. The waters that are attached to it, these waters are considered to be ligands. Ligands attach themselves to the metals. All right, ligands typically are neutral, all right, but they could have a charge depending on the type of ligand, okay? So, but for purposes for right now, the metal is in the middle of the complex, and then what surrounds it are considered to be the ligands. That's important. Any questions on this slide here? Do you guys remember the Le Chatelier's principal experiment where you formed that dark red blood complex?
Yeah.
Yeah.
Remember that you had iron and you reacted it with the thiocyanate SCN minus?
Mm-hmm.
All right, what color do you remember seeing after it reacted together?
It was like a darker red, and it started getting
Yeah,
lighter.
exactly. And so what's happening here is the SCN is actually attaching itself, and in fact, there's only one SCN because that's the way the complex forms, and this complex ended up being +2 overall because the SCN's minus. This is a complex. What we saw there was a complex. The metal ion was the center, and the SCN is the ligand. So the thiocyanate actually is the ligand that's attaching itself to the iron. Does that make sense?
Yeah.
Yeah,
Okay.
actually.
Awesome. Good. So the next thing here is when a complex ion combines with counter ions make the neutral complex called a coordination compound. Okay. So talk about complexes being coordination compounds. So there's two valences. Okay. Don't get confused with this. The first valence, which is the primary valence, is the charge of the metal. The second valence is the number of ligands attached to the metal itself. Okay. So again, the first valence is the oxidation state of the metal, the charge. The secondary valence is the number of ligands attached to it, okay? So when I'm talking about valences, that's referring back to the charges and how many ligands are attached to the metal. All right, so coordination numbers are basically representing how many ligands are attached to the metal. So if you have 6 ligands attached to the metal, then that means your coordination number is 6. If you have 1 ligand attached, then that means that your coordination number is 1. But that's not something that's common. So the coordination numbers ranges from between 2 and 12, with the most common between 6 and 4. All right. So here's an example of a coordination compound. All right. So what happens here is that this compound, this is how we draw it. This is how you look it up in the book, in the CRC handbook in the lab. But the actual coordination complex is referred to here, okay? So the complex itself is actually what's in the bracket. This here represents the counter ion. The counter ion basically neutralizes the complex, okay? So this cobalt is +3. So this complex has a +3 charge, where the chlorines have -1, so that's -3. 3 minus 3 equals 0. So this is representing the complex. Now when you look in the complex, you have 6 ligands attached to the cobalt, the water itself is a ligand. So you have 6 ligands. So that means the coordination number of cobalt is 6. So its secondary valence is 6. Its primary valence is +3. Because you have 6 ligands and +3 charge. So how would this look like in as a structure? So this is a good example of what it would look like. You have your cobalt in the middle, and then you have your ligands attached and a geometric configuration around it.